Great. Today we'll begin topic 3 of exponential functions, modeling growth and decay. So what are some situations that can model exponential growth is today, and decay will be tomorrow. All right, so here is our growth model. So labeling the important stuff. So when a real life quantity increases, so we're doing increases today, that will be the plus here, by a fixed percent each year, the amount in of the quantity after t years can be modeled by this equation. So looking at the equation, the A value is your starting number, so your starting amount. The R here is your rate, and usually the rate is given as a percent, but you need to change it to a decimal. Time is usually in years, so T right here is your time, your exponent. Usually it's in years, but it can have some other time period. And then this whole thing right here, from graphing, we know this is your base. The whole base is called your growth factor. So what is it growing by? So the first couple of examples we're going to do involve using the table, and then we'll go to using a word problem to set up the equation. So in example 1, it says, in parts of the U.S., wolves are being introduced into wilderness areas where they had become extinct. The population grew according to the table. So let's look at the table. All right, so what is the growth factor? So again, real quick, I'm going to write the model, A1 plus R to the T. The growth factor is going to be the base part, and the way that we find the base is we do the common ratio. So over here, if we divide the 60 by the 50, so we do bottom up. So we start at the bottom, 60 divided by 50, and we get 1.2. So from here to here, it's 1.2. And then we got to figure out the other ones. Now, because this is a word problem, it's an actual situation, these aren't going to be exactly the same, but they'll be pretty close. So if we divide all the other ones, I'm just going to do a few here. You can do the rest in your calculator. 50 divided by 41, we get approximately 1.21. That 9 is going to round it to 2. But again, the first part is pretty much the same as the other ones. So one more. If we do 41 divided by 35, we get 1.17, which again, if we were to make it go to the nearest whole number, so 1.17, or the one decimal place, that would round to 2 as well. So I'm just going to say the growth factor is 1.2. So this is going to be the base of our function here. This is the 1 plus R. So to find R, this part wants you to find the rate. To find R, you set the growth factor equal to the parenthesis part, 1 plus R, and you solve for R. So minus 1 minus 1. So this tells us that R equals 1.2 minus 1 is just 0.2. And we want to convert that to percentage. So if we multiply by 100, that's going to move the decimal place back twice, and it's a 20% rate of increase. So we're going to see the percent more on the next page where we do the word problems. All right, so if this pattern continues, we want to write an equation for the model. So we're going to have y equals, A was your starting amount. So how many did we start with? Right here is the first one. We started with 20 wolves. And then we multiply that by 1 plus R, And we already know the 1 plus r is the growth factor, which is 1.2. So 1.2, and we raise it to the x power, or t in this case because it's time in years. So that would be our growth model. So to answer part C, we're going to use our equation. How long will it take for the wolf population to exceed 100? So this is talking about the population. So this is y. So we want to see what x value gives us the first number over 100. So we're going to take our calculator and we're going to put this into y1. 20 times 1.2 to the x. And we're going to look at the table to see when is the first time it reaches 100. So in the y equals, we want to put 20 times 1.2 to the, make sure you do the caret sign, and then you use x power. And then if you look at the table, the first time that it passes 100 is right here at 103. So we would say that the time takes, t is 9 years, because that's the first time that it's over 100. So that's how we're going to approximate the x value, is by looking at the table. Eventually, we will solve for it exactly, but we cannot do that until we have logarithms. So right now, we're just using the calculator. All right, moving on to example 2. Again, using the table, but this time we have to use the graph to generate the table. So the following graph represents the population of a certain kind of lizard. All right, so what we're trying to do is we're trying to figure out these y coordinates. So at 0, that's this point right here, but I got to figure out what these count by. So if this is 50, 1, 2, 3, 4, 5 in the middle, so 50 divided by 5 tells us that each tick mark is 10. 10, 20, 30, 40, 50. So it starts with 10. Now we can look at the rest of the table for 1, 2, 3, 4, 5, 6. So if we look at 1, it's at 20 because it's the second tick mark. If we look at 2, it's right there underneath 50, so it's 40. And we're going to establish a pattern. So once we establish the pattern, we can just use the pattern. So at 3, it's right here. So if I count 50, 60, 70, 80 would be that one. So if we try to figure out the pattern, because we're going to need that number, consecutively, what's happening from 1 to get to the next? We're multiplying by 2. Multiplying by 2. So we can just generate the rest of the table by multiplying by 2. And then we'll check to make sure that's correct. All right, so right here, 80 times 2 would be 160. 160 times 2 is 320. And 320 times 2 is 640. So checking that, it doesn't go to 6, but it goes to 5. So 5 is at the very top. So if that's 300, this would be 310, and 320 would be here. All right, so then we want to make an equation. Copy the equation down. Y equals A 1 plus R to the T. The y equals is your population. A is your starting number. So what number do we start with? We start with 10 lizards. And then we do times. We don't know the rate, but we know the whole growth factor. The growth factor, this whole thing, is what we're multiplying by. So we're multiplying by 2, and then we're going to raise that to the t power because time is in years. All right, so what is the population in 8 years? We could just continue our model, our table to get to 8 because there's only 2 more, or we can use the equation that we generated here. So if we wanted to use the equation, the 8 years, the 8 is giving us time. So we're going to plug this into the exponent for t. So equals 10 times 2 to the 8th power. And this I can just type straight into the calculator. I don't need to go to y equals because it wants the y value, not the x value. So let me pull up my calculator. And again, just doing